So today we have the pleasure to welcome to our seminar Professor Weiwei. So she is Associate Professor of Mathematics at the University of Georgia in the US. Before joining the University of Georgia, Dr. Hu held a tenure-track position in mathematics at the Oklahoma State University from August 2016 to July 2019. She also held a postdoctoral fellowship at the Institute for Mathematics and its Applications, University of Minnesota, on the program Control Theory and its Applications, from September 2015 to August 2016, and a non-tenure track assistant professor position in the university in mathematics at the University of Southern California from August 2012 to May 2015. She received her doctorate in applied mathematics at Virginia Tech University in May 2012. Dr. Hu's current research interests include mathematical control theory of partial differential equations, control and estimation of flow transport systems, and computational methods for optimal control design. She has been awarded various grants from the NSF and the DoD. She was also awarded the Humboldt Research Fellowship for Experienced Researchers in 2024. So, Professor Weiwei, please, the floor is yours.
Thanks, Andreas, for your kind introduction. And so today I'm going to give an introduction, actually, control design for mixing in incompressible flows. The topic I have been working on in the past few years. This project has been supported by NSF and the Air Force. So, of course, first of all, I'm going to explain what's so-called mixing and how we are going to achieve good mixing, and how we construct our control for achieve like possible optimal mixing. So let's start. Are we? All right. So first, this is my outline for today's talk. So I think I have 2 hours, right? No. I'll try to keep it within 15 minutes. So I will start with the mixing phenomena, and we'll explain what's so-called good mixing. And then we mainly would focus on effective mechanisms for mixing. And then, of course, here, mathematically, we have to be rigorously talking about what we mean by good mixing, what would be a mathematical measure to quantify mixing. And then in the end, I'm going to focus on the control design, both open and closed control designs. So mixing, oops. Okay. I have to use my hands. So basically, mixing is to disperse one material or field in another medium. It occurs mainly in natural phenomena and industrial applications. Actually, we say this every day in daily life, like mixing in painting, mixing in baking. I guess everyone has this experience about this phenomenon. And from large scales, such as spreading the pollutant in the atmosphere and mixing of temperature salt and the nutrient in ocean, to small scales. For example, like nowadays, there's microfluidic devices is very powerful, which allow to significant progress in medical treatment and then like development of biosensors in, for example, DNA analysis. And then controllable and fast mixing is critical in practice, actually, for microfluidic devices, especially with light-on-chip devices. Then I have to back to the keyword mixing. So basically here mixing, as you've already sort of have a basic idea about this application I'm showing. So mixing means a physical process where both are stirring. So here stirring especially refer to the additive mechanism. Later on, I'm going to come back to explain more on this term. And then the diffusion occurs simultaneously. So now what do we mean by stirring? Stirring means the advection of materials, material blobs subject to mixing without diffusion action. So then let's recall what's called diffusion. Diffusion is the average effect of small-scale random particle motion. I guess we learned this in high school physics. Okay. And then based on this cartoon, actually, let's say if you look at the figure A, so say we have 2 fluids in contact with each other. And then they exchange molecules across an interface. Next, we have black and white stands for different fluids. So the molecules crossing interface between these different fluids activated by the molecule random action. So the figure A somehow shows like before starting exchange, the black and the white blobs start to exchange. And then here, figure B shows instantaneous state during the exchange. And then as you can imagine, like, although this random motion occur everywhere in the two fluids, but it does not really cause much difference for the same fluids which are far away from the interface. However, in the region near the interface, molecule on both sides have different properties, and random motion, the random molecule motion results in permission. If you look at the figure B, right? And then from one side to another side. So such permission is so-called diffusion. And then if you recall the so-called Fick losses, the flux of one species through the interface is proportional to the gradient of the concentration of those two fluids. And this proportional constant is then defined as a diffusivity constant. Okay? So the diffusion mixing can be made effective if there are sufficiently small blobs of one fluid immersed in the region of the other. And the length scale of these blobs reaches the diffusion length scales, then both blobs diffuse to the other fluids, resulting in good mixing. If you want diffusive mixing occur. So the diffusive scale of the blob itself is quite important. Otherwise, diffusive mixing is inefficient. Right? Then in summary, good mixing basically, especially here, I consider like low diffusivity materials occur in two stages. The first stirring in the first stage, and then diffusion in the second stage. So we'd like to sort of choose the property of the vective strategies such as chaotic stretching and folding, which lead to fluid blobs or fine filaments, and then the diffusion is able to kick in. Okay? But here in this talk, we're mainly focused on advection dominant case. So in this case, I'm going to assume molecular diffusivity is negligible. So only focus on advection mechanism for a mixing. Okay? And it is known actually, it's possible to utilize the purely advective mechanism to create an additional fluid velocity to obtain complicated mixing or chaotic mixing. Even the fluid itself is very regular. So in smooth fluid fields, one is able to achieve quite nice mixing if we introduce appropriate advective mechanisms, right? And especially time variation in the velocity may generate chaotic transport, in which it can be actually either or positive approaches to when you introduce this time variation. Now, what do we mean by active or positive approaches for mixing? Let's see. I believe these figures are quite familiar with. Like think about when you mix coffee with milk. So basically the active approaches means supply and energy to the system, right? So stirring, so you can use a spoon to stir the coffee with milk, then stirring a fluid back and forth can generate fluctuating velocity with respect to the flow barriers. Therefore, engender transport across them to achieve better mixing. Okay? Of course, you can buy something like this, it's more automatic, but I normally trust myself better. Well, so that is about the active method. So in contrast, the passive approach do not supply energy, but use passive mechanism to add velocity agitation. For example, one can have this bends or buffers or curves in the channel to possibly generate anomalous velocities. Okay. Even the flow in this curved channel, the velocity somehow keeps steady, but when the flow passes through such buffers, it's able to cross the flow barriers and generating transport. So in this case, it's so-called the passive mechanism for mixing. Then after all this sort of introduction, let's see, how can we mathematically come up with a measure to quantify the degree of mixing? So basically here, mixing, I always like to be well mixed, right? So to achieve good mixing. So think about it, the fluid trajectories are given by transport can be described by the transport equation, actually ODEs. And in fact, the equation 1 is a Lagrangian specification of the velocity field, representing the rate of change of position of each fluid particle given by its velocity, right? So this capital X stands for the particle, but time t and the position x. The motion of particle described by velocity. And solving the two equations, so given initial condition, the Lagrangian trajectory in the particles in the fluid can be determined. So we can follow the particle, right? Follow the velocity, track the trajectory of particles. And here, we like to consider the case where the flow map is area preserving or volume preserving. So here we assume our velocity field is divergence free. So in the case, say D equals 2, divergence free means the partial derivative of V1 with respect to x1 plus this component is 0, right? So that's divergence free. However, with this presentation, although we know the velocity of each particle, but does not give us information about mixing, right? Then maybe one of the ideas is maybe we can assign each particle value, let's say theta, at any time t and the position x, right? So theta here is a scalar, then which is conserved, move around in the flow, right? Let's see. I think I showed this picture many times in my slides. Initially, let's say we have a unit square containing two fluids, black and white, and I use one stands for black and the negative one stands for the white. So now I'm sort of assigned particle color. So the color 1, -1 is given by me. That's referred to the value of theta. Now, among all those 6 figures, you may tell the last one is best mixed in the sense, if you room in for each black dot, you see the white dot evenly distributed, vice versa, right? Then how can we describe what we have observed? So the last figure is the most homogeneous one among all the 6 figures. Then let's maybe consider the 1D case. Let's say if we have just 1D periodic interval, 0, 1, I'm going to define a metric D, which takes the average of my scalar theta at any point x and with any radius w half. And you average it. And then xw can take any values from 0, 1. Then we're going to define the Smith norm by averaging d squared over x and w. Okay. So it's basically like you want to pick any point in your domain and with any sort of room in, room out in any area, you want to say whether the fluid is mixed. And this metric or measure is precisely equivalent to the negative Sobolev norm, h -1/2 of your scalar field theta. So if this is the first time to say this norm, I'm going to explain a little bit more. For density field with Fourier expansion, we can always write theta in terms of Fourier expansion field to the domain, right? So here theta k hat stands for the Fourier coefficients, and this k here stands for the wave numbers. And then the h-1/2 norm is summation, is given by the series, right? And the k is the vector, so it depends on the dimension. So of course, in this case, my d is 1, so k is basically the scalar. And notice that the wave number is in the denominator when you have negative index here. Now, let's take a closer look of this Sobolev norm. Okay. Why this norm somehow can be used to quantify what we just described or observed, this homogenization process. So let's recall, let's say, now I'm going to look at this in the d-dimensional torus. Right? You can think about this in the periodic domain. With each dimension, the length is L. Oh, sorry, I put it 1. So the length is 1. And I'm going to assume the initial condition has 0, means the spatial integral is 0. Okay. So then if one look at the Fourier expansion of such scalar, then the zeros order is 0. So then we can somehow define the so-called homogeneous of the norm of index S by the following equation. Okay. This S for now can be any real number. So the homogeneous of the norm, HS, is given by the wave number takes the norm to the power 2S, okay, and then times the power 2 of the Fourier coefficients. Now, just look at case where if S is positive, then the norm actually put much weight on the higher frequency. And then that's a function that have a smaller fraction of their Fourier mass in the high frequencies will be less oscillatory, right? And then have a smaller HS norm. So you can think about if S is 1, that just says a gradient. If you have a energy conserved, let's say if theta is L2 conserved, and the gradient theta is bounded, that means certain smoothness, right? So that means the oscillator is not that bad. Now, in contrast, if you look at the case where S is negative, the norm actually puts less weight on the higher frequency. Then the function that have a larger fraction of their fluid mass in the high frequency will be very oscillatory. So this is actually what we want. If you recall the figures I showed earlier, black whites, they really merge very well. That means oscillation really bad between the black and white dots. Then to have a smaller HS norm means indicates sort of a very oscillatory scenario. Okay, this based on the expression about the homogeneous Sobolev norm, then and connect what we have just explained about this homogenization process, then it's reasonable to claim that the mixing of theta is equivalent to theta in terms of HS norm, where S is negative converge to 0 for every S. So basically, the mixing of theta is equivalent to the weight convergence of sequence when T goes to infinity. Okay. So basically here, when I write the HS norm converge to 0, so in terms of HS norm, where S is negative, there's a strong convergence, right? Strong convergence in negative Sobolev norm, but weight convergence in L2. Okay. So in fact, for any S smaller than 0, the quantity can be used as a measure of how mixed the distribution is at time t. Then, in other words, any negative Sobolev norm which quantifies the weight convergence can be used as a mixed norm. Okay, and then in fact, there's a more detailed study I listed in the references here. And in particular, later on, in my following discussions, I always consider S to be -1. Okay, to be computational convenience. Also, the H to -1 norm over L2, this stands for a certain scale. So I'm going to stay with HS equals -1 in my discussion. So the previous discussion is based on homogeneous Sobolev norm in theoretical domain. Then can we extend it to the general domain? Because later on, when we apply my control design, I would like to always work on general boundary domain. So in the general boundary domain, I'm going to consider the dual norm H1 prime of H1 space for quantifying mixing. Okay. So in this case, the H1 prime norm, basically, we can take the duality of F with any test function phi in H1. So we take this norm as the measure to quantify mixing. Okay. Any questions so far? Is everything clear? All right. Then I'm going to back to more mathematics. So now remember all the definition and then this ideas is based on the scalar field, or somehow we assign to the particles, right? Then record the total rate of change of the function theta as a fluid parcels moving through a flow field can be defined or can be described by the Eulerian specification of velocity, which is given by the transport equations. Okay? So basically, if you apply the characteristics, the Eulerian representation of transport equation will give us the ODE we showed earlier. Again, from now on, I'm going to consider my domain is open-bounded and connected. And then the domain boundary is sufficiently regular. Then here again, theta now stands for, say, in general mass concentration, density distribution, or the color of your tracer field. Now, velocity here, I'm going to assume it's incompressible, and with no penetration boundary condition. That is, divergence V is free, and the normal component velocity restriction of boundary is 0. So no fluids going out or enter. So the volume is conserved, right? And then in fact, one can use LP norm. Well, you can do the LP norm estimate, LP norm of your density field always equals the initial LP norm. This P can take from 1 to positive infinity. Okay, so basically have mass conserved. Then, so here I'm going to present some known results and open question in mathematical fluids. What's their sort of focus in this problem, or what they care about? So if we look at the transport equations, one of the problems here people care about is what exactly the relation between the velocity and the decay rate. Right? So the velocity field is actually we like to control or manipulate for achieving mixing. So of course, the first question is what's the relation? So in a paper by Alberti, Krapa, and Mazzucato in 2016, they said, okay, let's say assume the initial condition just essentially bounded, and then spatial value the mean zero. They actually also assume a similar structure. So they figured that there exists, let's say, velocity in WSP, so Sobolev space. The spatial derivative is of order S, and then it's P centrifugal. After take S order derivative is still LP integrable and uniform in time. S is non-negative, P is between 1 and infinity. Also can take the bounds, such that they show that if S is smaller than 1, for example, if the velocity in L2 in space, perfect mixing in finite time is possible, in the sense there exists a finite time such that when T approaches this P star, the mixed norm converts to 0. Okay. And then they showed if they improve the regularity velocity, let's say if S is 1, perfect mixing is no longer possible. They can show the polynomial decay, means the mixed norm decays polynomially. Okay. And then, sorry, exponentially. And also, Ogindi, Lisa, and Martini in 2023, actually very recent, this paper is still on archive. They constructed an alternating piecewise linear shear flow, which actually is ellipses in space and time periodic for exponential mixing. So this is one example they construct to demonstrate the exponential decay is possible for S equals 1. So ellipses is W1 infinity, right? Now, the question is, if one increase the regularity velocity field, let's say if S is strictly greater than 1, they showed that they can get polynomial decay. And back then it says was unknown whether the mixed norm decays exponentially in time for some S greater than 1. Okay. However, later on, Elginti, Gelatos, they showed actually the answer is affirmative. If S is greater than 1, smaller than 2, in particular, has an upper bound of 1 plus 5 half. And P is in this interval. They actually construct the velocity explicitly to show exponential decay is in fact possible. Okay. So then later I'm going to come back to those discussions when we incorporate the control theorems. But now I like to understand when I first say actually mixing problem back in 2015, Charles Doran is one of the early people looking at fluids mixing using mixed norm from University of Michigan. He gave a talk at the USC. So normally when they look at this problem, they always assume velocity satisfies the constraint and what would be the best mixing or optimum mixing. So I was thinking maybe we can incorporate the dynamics associated with velocity field, because in real life, velocity is always governed by some flow dynamics. So then my question is, how can we optimize mixing by active control of fluid dynamics? So as I explained earlier, mixing can occur in turbulence flows, as well as nominal flows with Reynolds number actually very small, can be even 1 or even less than 1. So I start with the setup, like we have a transport equation where velocity is described by the Stokes flow. So here, if you look at this equation, Stokes flow, this rho stands for the viscosity, P stands for the pressure, and then we again assume the flow is incompressible. And also later on, I considered the mixing value Navier-Stokes flow. So Navier-Stokes flow, here we have this nonlinear advection curve without gradient V in this equation, okay? And then the right-hand side, if you notice, we have F theta. So F theta stands for the local forces, such as the buoyancy, for example, theta times the unit vector in the direction of buoyancy, right? Then that's show the buoyancy. Now, I considered actually the most challenging case is the active, well, if you have these local forces act on velocity, we call the scalar field is an active scalar. Active scalar is rather challenging. In fact, if one, I don't know, anyone work on Bush-Nash equations. So if you look at transport equation coupled with the Navier-Stokes is a Bush-Nash equation with 0 diffusivity. And earlier Moffitt, in his earlier paper, he posed the open problem was asking with a gradient of theta, so gradient of the scalar field blows up as diffusivity converges to 0. Right? And then in the end, this answer was addressed in Thomas Ho's early paper, 2005. They said, okay, there's no blow up for the gradient of theta. And later on, when there was a post at the USC, we further showed gradient theta actually has no blob for initial contingent theta in H1 and the velocity in H2. Okay, so the reason is later on when we apply our control design, it's very important to understand the well-posedness of the governing system itself before we do anything. Right. All right. So then, for example, let's say if how can we introduce our control? So let's first look at the flow governed by the Stokes equation. So keep in mind here, I said velocity has to be divergence free and the normal component is 0. So no fluids enters through the boundary. Now, how am I able to introduce the control? Of course, one can think about stirring the fluids inside of your container or vessel, then that leads to internal control or distributed control. But when I work on this, it's motivated by the observation that moving walls accelerate mixing compared to the fixed walls with no safe boundary condition. The reason is, I think everyone may have the experience when you mix in flour with water. If you just stir the fluids in your container, and then the boundary might have thick sort of layers, the boundary layers, the mixing couldn't cross, right? So that's what I mean if you have a fixed container with no safe boundary. You may have like boundary layer phenomenon. The mixing only occurs in the center area. Now, if you move in the wall or stir the fluids along, sometimes we mix the flours. You may want to, okay, I'm going to stir along the thick boundary so that the mixing can cross the boundary layers. Then if you sort of rotate the wall, that's going to create a closed orbit near the boundary of your domain so that you have much better mixing region. So that's the idea. So therefore, I consider in the tangential direction, I'm going to assume the fluid is able to slide along the boundary and against a certain friction. So there's a friction term, which is against the velocity. So this dV stands for the deformation tensor, which is the average gradient V plus gradient V transpose. And the n tau again is normal and the tangential vectors. So now I'm going to assume tangentially, I'm going to stir my fluids, and this G stands for my control input. Okay, I'm going to introduce the control along the boundary, and then so that I can control my velocity field. And therefore, via the advection term, I can steer the behavior of my theta. So that was my design. So as I said, so boundary control, you can introduce control via the boundary, and then you just simply stir the fluids in the interior that's introduced, that leads to an internal control. Then we can always formulate this abstract Cauchy problem, right? When we have a controlled system. So again, I have a transport equation, and then the second equation is abstract ODE form for my velocity field. And then here, okay, let me explain a few terms here. So this A actually is the Lu is the viscosity times the ray projector act on my Stokes operator, act on my the Laplacian operator. So this is the Stokes operator associated with appropriate boundary condition. As I said, we are going to say the normal component is 0. So the ray projector essentially maps the L2 functions into divergence-free subspace and with this boundary condition. And then if we consider, say, number Stokes, then this NV would be the negative ray projector act on this advection term. And then if this term is 0, then we have a Stokes equation. Then this U stands for control input. B is the control input operator, depends on how you like to introduce a control to the system. So I'm going to work on this abstract formulation stands for, let's say, the linear control for Stokes or Navier-Stokes equations, and then via advection term, I'm going to control theta. So that's sort of the basic formulation for the problem I'm going to consider. And then the natural sort of as a first step, I would like to say, okay, how can we formulate the optimal control problem for achieving optimal mixing? Let's say we can consider for certain given capital T, like to minimize the mix norm at T equals capital T, as well as the mix norm over the time interval from there to capital T, with say minimum cost of my control input. And then, of course, it's quite subtle to determine what should be the suitable control input space for you. Because when we choose this admissible set of control, one needs to, first of all, make sure my control is physically meaningful. And also need to make sure the problem P subject to my PD constraint is solvable, right? It's well posed. And then very also often we need to use the first order automatic condition to solve the optimal control. So we may want you have certain smoothness so that the solution is allowed the Gateau differentiability with respect to my control input, right? So student issue is quite important and sometimes can be a little bit challenging, right? Especially for we have like the active scalar field, the two-way coupling makes the problem rather challenging. Okay. Now, how can we rewrite this mixed norm in a more transparent representation? Now, H1 prime, so in order to deal with this norm, I'm going to introduce the eta, which is the higher regularity counterpart of theta, by solving an elliptic problem, right? So I'm going to solve eta through this elliptic problem with Neumann boundary condition. So here I add identity just to make sure the Laplacian has no zero eigenvalue in this spectrum, right? So now negative theta plus I is invertible. Then I can define its square root, and I write this as lambda. Then the mixed norm H1 prime is can be written as lambda inverse arctan theta, and then you take the L2 norm, or the H1 norm of the eta. Okay, so I can rewrite this term in terms of my eta. Now, okay, I'm going to back again, talking about the challenging we have encountered in analysis and computation for solving problem P. So first of all, the nonlinearity coupling due to advection essentially leads to nonlinear control and a non-convex optimization problem, right? So normally we don't have any uniqueness unless you impose certain smallness condition on the data associated with the problem. And then zero diffusivity in my transport equation, that's the key challenge we encountered, because differentiability leads to very high order regularity required for velocity field. Okay, and if one considers boundary control, then the creation of vorticity on the domain boundary and also the compatibility condition may come into play, even in the case of non-smooth solutions. So here, what do I mean? Compatibility means initial condition restricted on the boundary has to be the boundary condition when t equals 0. So if we have to address the compatibility condition, basically you introduce addition layer or addition constraint to the control. That's something we don't want. However, in the case where we have the transport equation coupled with the Stokes square, another Stokes equations where f theta, this is the buoyancy term, for example. The problem is rather challenging in the sense we need to find the appropriate state space such that the governor system is well posed and also somehow allow the first variation of the system is well posed, right? And then since we have quite high regularity required for velocity, and then that leads to high regularity for initial and the boundary data. So choosing the appropriate state space is very extremely important in this case. And the computation. Now, first of all, when you solve the number Stokes, and then we need to make sure the divergence-free condition holds, so that the mass is conserved for the transport equation. So find the appropriate numeric scheme for mass conservation in incompressible flows is very important. And also during mixing occur, small scales like fine filament and the large gradient of the scalar field is going to develop. So like when you try to capture this mixing process, one really need to refine the mesh. The computational is really, really costly. And then furthermore, if one want to do the optimal open loop control, then we know that when we solve this optimal control problem, this result in a state equation about theta, right? And then the joint equation about the Lagrange multiplier, actually you introduce a system to solve the optimal control problem, which joint equation has to be solved backward in time. And we also have a nonlinear automatic condition. So solving the entire automatic condition for finding the optimal control requires solving state equation forward in time, and then the joint equation backward in time, and coupled with nonlinear automatic condition. So, and then we have to store all the data. So computation is rather costly. Then, so can we somehow construct something is optimal in certain sense, but also computationally less costly. So I would like to mainly focus on the feedback control we considered in this work. So let's first look at the case where the velocity field is governed by Stokes flow. So basically, I don't have this nonlinear direction term, and here I don't assume any sort of the force from theta act on the velocity. So just a one-way coupling. Okay, so I'm going to consider transport equation with a Stokes equation, and here this simple elliptic equation is just to address the mixed norm. Well, we know, I mean, solving optimal feedback, one can use Hamiltonian Jacobi equation, right? But that very often needs to very high dimensional, like needs really computation with dealing with high dimensional equations. Now here, instead, we're going to consider so-called instantaneous control design. Okay, so later on, which you will see this is like an approximation of an open loop control. So this design actually is closely tied to receding horizon control, RHC, or model predictive control, MPC, with fine time horizon. So the idea is, let's say, we consider, first of all, the uniform partition of time interval 0 to capital T, and then we let this H be T, the final time capital T, divided by the number of intervals. And then I'm going to use a semi-implicit Euler method in time for discretizing my governing system. Okay, so for example, here, I'm going to discretize theta, the time derivative of theta, use just Euler's method. And then for this nonlinear term, I use explicit form for theta, implicit form for V. Okay, so similarly here, I use implicit for my Stokes term V here, and also my control term. Okay, so after discretization, now I'm dealing with the stationary system, right? Then the cost functional, I just like to optimize the cost functional over one time step. The previous setup, like you're looking at the optimal control for the cost functional, you want to minimize it over the entire interval from 0 to capital T. Now I just want to do one-step minimization. I solve this optimization problem just by one step in time, and then march forward. And then through this recursive procedure, I'm able to derive something quite interesting. So do one-step optimization, actually, you will realize this is able to connect the joint state with the state. That's why we are able to close the loop, just one step. And then by recursive approach, one can show that the semi-implicit time discretization actually equivalent to the closed loop system look like this, right? So now keep in mind, this H actually is the time step we take initially to discretize the system. In the end here, when we close the loop, if you look at the continuous level, so this entire procedure is a discretization of this closed loop system. And here now this H is a fixed parameter in my new continuous closed loop system. And then in fact, we have a feedback control law here. U is given by control weight gamma, and then it's -1, this H, the step size, and then B is the control input operator, okay? And then B star is the joint operator, and times I minus step size H times the Stokes operator take inverse, and then act on the lower projector of theta times greater than eta. So this control only depends on state variables, okay? But since here, this procedure has a lot of approximation, so we get a suboptimal control. Okay, so that's my closed loop design. Then a couple of questions we need to address here. Is the closed loop system stable? Well, I probably should say whether the system is well posed and then whether it's stable, okay? So now let's look at the closed loop. As I said here, the B in theoretical is a control input operator, but when we show the well posedness and the stability, we have to assume the B is sort of an identity operator. So basically, in this case, we assume we have to sort of stir the fluid everywhere in the domain. This condition is a little bit strong, but this is what we can get at this point. So now we have an internal control. And then if I replace the U by my control law. So I have a closed loop system, and one can show the well postness. So if the initial condition theta naught in the intersection of L infinity and H1, the velocity is in V2, we get the well postness and then the regularity of the solution in space here. So V actually is up to it's sort of H3. Oh, by the way, I probably forget to mention what this notation means. So this notation means divergence free of the subspace of H3, sublevel space H3. So it's quite smooth. This is because this operator, right, is like Laplace inverse, smooths out the velocity field. That's why here is quite smooth. And again, this inverse operator is really due to the discretization scheme we used. Later I'm going to show you with different discretization scheme, this guy may not be there. Okay? Now, this is well postness. And in fact, when we show the stability actually is quite challenging. Well, if one look at the total energy, right? I mean, total energy is in terms of the mixed norm and the H1 norm velocity. Now, the total energy rate of change actually is strictly negative. So this guy is bounded by H1 norm of velocity, okay? And this is a negative sign here. The total energy actually is decaying. But here we only have information about the velocity. We don't have any information about the scalar field, okay? So what we did was we analyzed the stability of velocity in terms of it's L2, H1, even H2 norm, and the time derivative even in terms of L2 norm converges to 0. And then we look at the transport equation to get the stability of my scalar field. So in the end, what we can show is the scalar field actually in terms of H1 norm decays and converges to a certain constant smaller than initial distribution. Of course, in this case, the control converges to 0. So we get the stability, but we don't really know the decay rate of the velocity field and the mixed norm, our initial work. And later on, we actually was able to show the polynomial decay using semigroup theorem and the nonlinear analysis. We're able to show if we make certain answers of the velocity field, if we assume velocity somehow decays of a polynomial order, then we can show the mixed norm and your control also decays polynomial rate. Now I'm going to briefly represent our numerical experiments. So when we solve the closed loop system, we have sort of transport coupled the flow equation, and also we have an elliptic equation. So where we use Taylor-Hood is a classified element method with a projection method for solving Stokes equation, and time-wise we use backward discretization of order 2, okay, solving Stokes. And then for transport equation, we use Runge-Kutta discontinuous Galerkin method with third order in time. Then here is a forward simulation. We assume initially, well, our domain, first of all, is a unit disk. Initially, we have bicolor fluids, and the initial distribution is hypertangent, y over 0.1. We just like to smooth out the interface. Because for initial data, we need it's in L infinity intersects with H1, so we need some smoothness of the initial data. And then, so the parameter H, this time step size, we take 0.1, and then the control weight is 10 to negative 6. So that you can see how the mixing occur and the mixing process. You really see the fine sort of a filament appear in your domain. And then of course, a large gradient of theta encountered here as well. Then if you look at the mixed norm actually somehow decays following t to negative 0.5, the polynomial decay. And then we try different h. Let's say the first row is when h is 0.01, so we have a smaller sort of time step size when we discretize the original system. And then the second row is h is 0.1, the last is 1, different time scales. At this point, we can only claim our feedback control is suboptimal, but we don't really know its optimality. Okay? Although we try different sort of parameters, and then it's hard to really say how optimal this feedback law we constructed. And I mentioned earlier, use different numeric scheme to discretize the governing system. We may get different sort of regularity of your control. Now, for example, here, if we apply explicit Euler discretization for the Stokes term here. And then in the end, we get the control law without this inverse Stokes term. So less smooth compared to the previous approach, okay? Then we actually get more chaotic mixing result for different H. And then again, in the end, we did the approximation of the mixed norm using different control laws, and then with different discretization parameters, we observed the all decays with the polynomial rate. Right. So that's about the closed loop system. Actually, I think this part I showed very briefly in 2022 when I visited FAU the first time. And then Enrique was suggesting maybe we can first just focus on the transport equation and determine the velocity field, which achieve mixing with no dynamics. And then we know how to sort of control the Stokes or Navier-Stokes flow. Then we approximate the desired velocity field by active control of the flow dynamics. Okay. So far, I mainly focused on, let's say, how can we optimize velocity along no dynamics for this point. And then I have a few questions listed here related to the open problems I mentioned earlier. Now, again, let's say if we have a periodic domain and with initial data mean 0, okay? Again, I'll assume velocity is of this regularity here. Now, if S is smaller than 1, and for any T star, okay, for any T star, can we always construct feedback flow, which only depends on theta and the eta, right? Such that perfect mixing can be achieved. Right. So like I mentioned earlier, if S is 0, it's possible there exists, right, T star, the perfect mixing is possible. But here I'd like to ask for any T star, can we always construct feedback flow? Makes this possible. And then for S greater than or equal to 1, can we always construct feedback flow such that exponential mixing is possible? So basically, the mixing decay follow this exponential rate. So that's a question I put in the end, and then I guess that's the end of my talk. Let me know if you have any questions.